Lesson number 4, Square Roots, Pythagorean Theorem, and Real Numbers. To begin, let's look at the key concept of square roots. A square root of a number is the value that when multiplied by itself will yield that number. The radical sign, as shown here, indicates that we are finding a square root. For example, the square root of 16 equals 4 because 4 times itself is 16. The number under the radical sign is called the radicand. The next key concept deals with perfect squares. If the square root of a radicand is a whole number, then the radicand is said to be a perfect square. Here is a list of the first 12 perfect squares. That brings us to our first example. Example number 1. Find the square root of 900. To do that, we'll be using our calculator. And we need to use our square root button, which is located right here. X squared. Second function is the square root. And we'll start by hitting the second function button, and then we'll hit that square root. It opens up a parentheses where we can type our 900. And I'm going to highly recommend that you close the parentheses each time. If you don't close a parentheses, then the calculator closes it where it thinks it should close it. So in this case, it wouldn't have made a difference. We hit equals, and it gives us a result of 30. So the square root of 900 is 30, and that's our final answer. And here's the solution typed up, which brings us to pencil problem number 1, and its solution is shown in a separate video. Next, we look at the square roots of fractions. When evaluating the square root of a fraction, we take the square root of the numerator and the square root of the denominator and express the result as a fraction. Here's an example. Example number 2. Evaluate the square root of this fraction. To do this, we want to remember our rule that says the square root of a fraction equals the square root of the top over the square root of the bottom. So we can take the square root of a fraction, a over b, by finding the square root of the numerator and the square root of the denominator separately. So in this case, this equals the square root of 25 all over the square root of 121. If we use our calculator, we hit the second function, and then it's the shift of the x squared button. We type 25, close parentheses, equals, and that gives us 5 for the top. And then repeat that process. We'll hit clear, second function, square root, 121, close the parentheses, hit equals, and that gives us an 11 for the denominator. 5 over 11 does not reduce, so that's our final answer. And here's the same solution typed up, which brings us to pencil problem number 2, and its solution is shown in a separate video. Now we're going to look at approximating square roots. We can approximate the square root of a number that is not a perfect square by estimation or by using a calculator. First, we're going to look at estimation. To approximate the square root of a number that's not a perfect square by estimation, we're going to find the nearest perfect squares that lie above and below the radicand. Here's an example. Example number 3. Find the two whole numbers that the square root lies between. We have the square root of 87. We'll look at how to do this problem with a calculator in a future example, but for now we're going to do it by estimating. In order to estimate, we want to recall that we have a few square roots that work out to be whole numbers. The square root of 81 is 9, and the square root of 100 is 10. If you don't have these memorized yet, you can refer to a list, but these are some numbers that you'll want to get used to. So our value, the square root of 87, must fall between the square root of 81 and the square root of 100, and therefore, when we go to calculate it, it has to be 9 point something. And again, we'll use a calculator in a future example to get those digits more precisely, but for now we can see that the square root of 87 must lie between the whole numbers 9 and 10. So the square root of 87 lies between 9 and 10 is our final answer. Here's the printed solution of that example. And now we come to pencil problem number 3, and the solution is shown in a separate video. Now we're going to talk about rounding a decimal number. We use the same basic rules when rounding a decimal number as we do with a whole number. In general, there's two possibilities when rounding the decimal portion of a number to a given place value. If the digit that's immediately to the right of the given place value is 5 or greater, we'll round up, as described here. If the digit that's immediately to the right of the given place value is less than 5, we'll round down, as explained here. As an example, let's look at 73.6974, and let's round it to the nearest hundredth. First, we have to identify the hundredths place, which is where the arrow is pointing at the 9. It's 2 places to the right of the decimal point. And then we have to look 1 place to the right of that, which is the 7 shown in the box. Since 7 is 5 or greater, we're going to round up as described here. We add 1 to the 9, which bumps it up to a 10, so we leave a 0 in the hundreds place and carry a 1 to the 6 that's in the tens place, making it a 7. Thus, the nearest hundredth is 73.70. Now that 0 is no longer a placeholder, so we can simply write it as 73.7. We can also approximate square roots by using a calculator. Be careful not to confuse the square root button on your calculator with the square button on the calculator. Next example. Example number 4. Use a calculator to approximate the following square root. Round to the nearest 10,000th as necessary. So here goes. As we saw before, we can use our calculator to get this started. We're going to type the second function, and the shift of the x squared button is your square root key. Type the 87, close parentheses, and hit equals. And we get 9.327379053. Your calculator may show more or less digits at the right end of this number. It's asking us to go to the nearest 10,000th. The nearest 10,000ths place, remember this is tenths, hundredths, thousandths, 10,000ths. So this, 4 places over, is the 10,000ths place. To know how to round it, I have to look 1 place to the right, and that will tell me what to do with my 3. Since 7 is 5 or more, I'm going to round that 3 up to a 4, which will result in 9.3274. And that is the square root of 87 rounded to the nearest 10,000th. And here's that example typed up. Pencil problem number 4 is shown in a separate video. The triangle angle property says that the sum of the 3 angles in any triangle is 180 degrees. In right triangles, one of the angles is a right angle. That angle measures 90 degrees. In a right triangle, The side opposite the right angle is called the hypotenuse, shown in red. And the other two sides are called the legs, shown in red. We often label the hypotenuse with C and the two legs with the variables A and B. Which brings us to the Pythagorean theorem. The square of the hypotenuse of a right triangle equals the sum of the squares of the two legs. Using C for the hypotenuse and A and B for the two legs, we have the following relationship. C squared equals A squared plus B squared. The hypotenuse squared equals the sum of the squares of the two legs. This theorem can also be written in the opposite order with the hypotenuse squared on the right side. A squared plus B squared equals C squared. The square root theorem states that if x squared equals a, where a is a constant, then x equals plus or minus the square root of a. For example, if x squared equals 25, then x all by itself equals the positive or the negative of the square root of 25, which means it equals the positive or the negative of 5. Now we're going to look at solving for the hypotenuse in a right triangle. When the hypotenuse is unknown, we substitute the values of the legs, A and B, into the Pythagorean theorem and solve for the hypotenuse, C. Note that this process will involve using the square root theorem. Since the solution is the length of a side, we will keep only the principal or the positive square root. Let's look at an example. Example number 5. Find the missing side in a right triangle where one leg is 7 inches and the other leg is 24 inches. Let's start by making a sketch. The precise dimensions of this triangle are not as important as how I label it. So notice that I'm signifying that it's a right triangle by showing the right angle symbol. And these are the two legs, so I'll let the shorter one look like it's the 7 inches. And the longer one is 24. So again, it's not important if this is to scale, but we can continue on to try to find the missing side, which we'd call the hypotenuse. And typically we label that with a C. Since we're looking for C, when we write the Pythagorean theorem, I'll write it with the variable I'm looking for on the left. C squared equals A squared plus B squared. That's the Pythagorean theorem, and I'll start to substitute into it. C squared equals, it doesn't matter which of these two legs you call side A and side B, so 7 squared plus 24 squared. Continuing on, 7 squared is 49 plus 24 squared. I type 24. Now remember, we don't want to confuse squaring a number with taking its square root. At this point, we want to square it, so I simply hit the x squared button. It shows me 24 squared is 576. Continuing, I add these two numbers together, and I used my calculator to give me 625. And now we have c squared by itself equaling 625. So the next step is to say that c equals plus or minus the square root of 625. The plus or minus is not actually necessary because in this particular problem, because we know we're looking for a side, and that side has to be positive. So if you skip this part intentionally, but note that if it wasn't a triangle, there may be instances where the answer would be the negative solution. So c equals, I'm going to just keep the positive solution for the reason stated, and I'm going to find the square root of 625. I type second function, and I hit the x squared button, but by hitting that second function in advance, it gives me the square root. Type 625, close parentheses, hit equals, and it gives me 25. because this is a word problem talking about a triangle, I want to check out the dimensions are in inches, so this would also be 25 inches. And notice that that hypotenuse of 25 is the longest side in this triangle, so that helps let us know that this is our final answer. And here's the same example typed up, which brings us to pencil problem number 5, which is shown in a separate video. Next, we're going to look at the addition property of equality. Essentially, it says if two quantities are equal, if A equals B, then if we add an equal quantity to both sides, then A plus C equals B plus C. We can show this vertically by showing A equals B and then adding C to both sides, which gives us A plus C equals B plus C. We can use this property to help us solve for the unknown in an equation. In this case, if 9 equals 5 plus x, then we can subtract 5 from both sides. On the left, 9 minus 5 gives us 4. On the right, 5 minus 5 cancels out. Technically, it gives us 0, and 0 plus x is just x. And we're left with 4 equals x, so we've solved for x. Solving for a leg in a right triangle. When the hypotenuse and one leg of a right triangle are shown, we can use the Pythagorean theorem to solve for the unknown leg. Substitute the values of the hypotenuse c and the known leg into a squared plus b squared equals c squared. Notice when it's one of the legs that we're looking for, we typically put a squared and b squared on the left side of the equation, so our unknown is already on the left. We then solve for the unknown by using the addition property of equality and then the square root theorem. Here's an example. Example number 6. Find the missing side of the given right triangle. In this example, the missing side is one of the two legs. So when we write the Pythagorean theorem, I'll write it with the a squared plus b squared on the left, because I want the variable that I'm looking for to be on the left when I go to solve this equation. So a squared plus b squared equals c squared. The sum of the square of the two legs is the hypotenuse squared. And now I'll substitute some values in. I don't have any choice but to make this side c. That's the hypotenuse, so that equals 11 squared. With a and b, it wouldn't matter which of these I call a and which of these I call b, so I'll call this side a and this side b, as long as a and b are my two legs. So I get 7 squared plus the unknown b squared equals 11 squared. Using my calculator, I can simplify 7 squared to be 49 and 11 squared to be 121. Be careful, I know we're using square roots and squaring numbers within the same context, so you need to make sure that you're deliberately knowing which buttons you should be pressing. And now, notice that we want b squared by itself and eventually b by itself, so we'll begin by getting rid of the 49. Since they're adding this 49, and it's a positive 49, we'll do the opposite, which is to subtract. Recently in the course, we've often divided both sides by a number, but that was when something was being multiplied by that value. Here we can subtract 49, they cancel, giving us b squared on the left, and on the right, 121 minus 49 is 72. So if b squared equals 72, then b equals the square root of 72. We've been talking about whether or not we need the plus or minus. Again, since this is representing a side and a side has to be positive, I can deliberately leave out the possibility of the negative. And so I'll continue by using my calculator. And on my calculator, I type second function, the square root button, 72, close the parentheses, equals. Notice that up in the directions it said round to the nearest thousandth. The thousandths place is 3 places to the right: tenths, hundredths, thousandths. To round to the nearest thousandth, I want to look at the next place to the right, and it'll tell me what to do with that 5. Since this 2 is 4 or less, I'm going to leave this as a 5. And so B equals 8.485. These M's stand for meters. It's the same units as it was for the sides, so that is our final answer. And here's that same example typed up. That brings us to pencil problem number 6, which is shown in a separate video. Finding the diagonal of a rectangle. The diagonal of a rectangle is the line segment connecting two opposite corners. To find the diagonal of a rectangle, we can make a sketch and recognize that the diagonal is the hypotenuse of the two resulting right triangles. We can then solve for the hypotenuse. Here's an example. Example number 7. The screen of a television set measures 41 inches wide by 23 inches tall. Find the length of the diagonal to the nearest tenth of an inch. Let's begin by making a sketch of the television and its diagonal. It says it was 41 inches wide and 23 inches tall. And we're looking for the diagonal, which would be the hypotenuse of this lower right triangle. If I'm looking for the hypotenuse, then when I go to use the Pythagorean theorem, I'll use the version that puts c squared, the hypotenuse squared, on the left. Which version, whether the a squared plus b squared is on the left or right, it actually doesn't matter. You can get the correct answer either way, but we often like to have the variable that we're looking for, the unknown, to be on the left. Substituting, it doesn't matter which of these two legs I call A and which I call B, as long as they're both the two legs in our formula. So 41 squared plus 23 squared. Get my calculator to help me with that. 41 squared is 1681 plus 23 squared is 529. Continuing, c squared equals the sum of these two values. Again, I'm using my calculator, and that gives me 2210. So therefore, c, if I take the square root of both sides, c squared gives me just c. And on this side, it's a length, so I can ignore the negative and just find the square root, the positive square root of 2210. Let me go ahead and do that one on screen. Let's see, second function. I hit the square root button, type 2210, close parentheses, hit equals, and I get 47.01063,709. It asks me to round this to the nearest tenth of an inch, and so that's the tenths place. So I'm going to look at this next place to the right, and it'll tell me what to do with that 0. And since 1 is 4 or less, I'm going to leave that as a 0. So C equals 47.0, and this problem, the units was inches. And that's our final answer. And here's that same example typed up. Pencil problem number 7 is shown in a separate video. Real numbers. There is a one-to-one correspondence between any real number and a point on the number line. We can plot real numbers on the number line. For example, -7, -2, and 3 are plotted as shown. We can compare real numbers by using a number line and plotting each number on the number line. the numbers increase in value from left to right on the number line. Here's an example. Example number 8. Place a less than, a greater than, or an equal to between the two given numbers. We're going to use the number line to help us see which of these two numbers is bigger. So I'll draw a portion of the number line. Looks like I need a lot of negatives, so maybe I'll do 0 and 1 going that way. And so -1, -2, etc. -3.2 is a little beyond -3 going in the negative direction. And -6.5 is halfway between -6 and -7 going again in the negative direction. And so the further to the left, the smaller the number, the further to the right, the greater the number. So when we're determining the symbol, we read this from left to right. -6.5 is less than -3.2. And here's that same example typed up. Pencil problem number 8 is shown in a separate video. We can rewrite inequalities using an opposite perspective. Essentially, if A is less than B, then B is greater than A. Here's an example. Example number 9. Rewrite the given inequality using the opposite perspective. In this case, our original statement is 8 is greater than -14. To write it with the opposite perspective, we'll start with the -14 and end with the 8. And if 8 is greater than -14, then -14 must be less than 8. So you reverse the two numbers and you reverse the order of the inequality. And that is our final answer. And here's the example typed up. Pencil problem number 9 is shown in a separate video. Now we'll look at the roster form of a set. A set can be written in roster form by separating the elements with commas and enclosing the set with braces. For example, the set of the colors in the American flag can be written as shown here. The braces are on the outside, and red, white, blue are listed in roster form. There's also something called set builder notation, which is sometimes necessary. A set can be written in set builder notation by using the following format. We open a set brace, we state a variable, the vertical line is a symbol that means such that, and then we put a rule that defines whether something is in the set or not in the set. So we can read this as the set of all x such that x fits this rule. For example, this set can be read as the set of all x such that x is a color in the American flag. The following are classifications for important sets of numbers. The natural numbers, which we signify with a uppercase N, equals 1, 2, 3, and so forth, going in the positive direction. The whole numbers, which we signify by an uppercase W, are similar, but they also include 0. Integers, which we signify with the letter Z, because that's the first letter of the word integer in the German language, and they were some of the first to play with this. Notice that they're similar to the whole numbers. They include 0, 1, 2, 3, but they also include negatives, -1, -2, -3. Notice that none of the sets that we've looked at so far involve any fractions or decimals. Which brings us to the rational numbers, signified by the letter Q from the word quotient. It's shown in set builder notation, the set of all x, such that x can be written as the ratio of a over b, where a and b are both integers, and the denominator b is not equal to 0. Now we look at the irrational numbers, signified by the letter h, and they are the set of all x, such that x is a real number and x is not rational. Finally, we look at the real numbers, signified by the letter r, using set builder notation, that's x, such that x is rational or irrational. Note that all natural numbers are contained in the set of whole numbers. The natural numbers, 1, 2, 3, are contained in the whole numbers because 1, 2, 3, etc. are all inside of the whole numbers. Furthermore, all whole numbers are contained in the set of integers. As shown here, the whole numbers, 0, 1, 2, 3, and so forth, are contained in the set of integers, 0, 1, 2, 3, and so forth. Notice the integers have more numbers, other elements in that set, but they're contained. The whole numbers are contained within the set of integers. All integers are contained in the set of rational numbers. The integers, which do not have any fractions or decimals, are contained in the set of rationals. All rational numbers are contained in the set of real numbers. Rationals are all within the reals. Also note that in our course, irrational numbers typically involve square roots or special numbers such as pi. Which brings us to an example. Example number 10. Identify which of the following sets contains the number 17 as an element. Natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers. To begin, it's helpful to take a look at the sets that we're talking about. So notice that 17 is an element of the natural numbers because the natural numbers are 1, 2, 3, etc. in that direction, so it contains 17. Likewise, the whole numbers start at 0 and count up, so they'll also contain the number 17. And the integers are similar, 0, 1, 2, 3, etc., but they also contain the negative numbers, and which doesn't matter to us in this problem. The important thing is that 17 is an integer. Next, we look at the rational numbers, and notice that even though this says a over b, and 17 is not currently written as a fraction, 17 can be written as a fraction, and it has to be written as a fraction where these two are both integers. A and b, top and bottom, are both integers, and the bottom's not 0. So we're able to write this as an integer over an integer, and the bottom's not 0. So 17 is a rational number. Next, we're looking at irrational numbers. Those are numbers that typically involve square roots or the number pi, a few other numbers like that. But the other clue we can use is that a number is always either rational or irrational. Any real number is always either rational or irrational, but never both. So as soon as we know that 17 is rational, we know that it is not irrational. Those two answers always come with one and the other. So if we had a number that was not rational, then it would be irrational. And then finally, every number we're studying in this course, including 17, will always be an element of the real numbers. And so this number is an element of all of these sets, except it is not an irrational number. And that's our final answer. Here's that same example typed up. Pencil problem number 10 is shown in a separate video. Next example. Example number 11. Determine whether each statement is true or false. Part A, the statement is, every integer is a rational number. To help us with these statements, it's nice to know the various sets and what they contain. And so let's look at the integers. The integers are 0, 1, 2, 3, and the same pattern in the negatives. And we're wondering, are these contained within the rational numbers? And the answer is yes, they are. So this one's going to be true. Every integer is a rational because any integer, such as 3, could be written as 3 over 1. And therefore, you can write any integer as the ratio, as a fraction, a over b, where the top and the bottom are both integers, and the bottom is not equal to 0. So part A is true. Let's move on to part B. Is the fraction negative 2 pi over 7 a rational number? True or false? Well, that's going to be false, because even though right now it's written as a fraction, and that's what we want for a rational number, it says that the top and the bottom have to be integers. And a number such as pi is not an integer. And so that is the thing that tips us off to the fact that this number is not rational, rather it's irrational, and therefore the answer to part B is that the statement is false. Example 11 is also shown typed up. This brings us to pencil problem number 11, which is shown in a separate video. This brings us to the key concept known as absolute value or magnitude. The absolute value of a signed number is the distance that that number lies away from 0 on a number line. Absolute value is symbolized by using two vertical bars, and we put the number inside. For example, the absolute value of negative 7 is 7. This is because the distance from negative 7 to 0 on the number line is 7 units. We can now use that concept to help us compare real numbers that involve absolute values. To do such an evaluation, we will first evaluate the absolute values and rewrite the comparison. We can then use a number line to compare the resulting numbers. Notice that using a number line is optional. We will show it both ways. And here's the final example. Example number 12. Place a less than, greater than, or equal to between the two given numbers. To begin with, we need to evaluate this expression because it has an absolute value. And so the absolute value of negative 9.7 is simply 9.7. The distance that negative 9.7 is from 0 on a number line is 9.7 units. I'll leave some space, and we have to compare that to 4.8. Now, some of you may be able to finish off the problem right now by noticing and realizing that 9.7 is greater than 4.8. If you want to use the number line to be sure, and it looks like I'm going to need a lot in the positive direction, One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That ought to do it. And when I plot these numbers, I don't have to be super careful. The number 4.8 is more than 4, less than 5, closer to 5. So I'll put it about there. 9.7 is just this side of 10. And I can see that this number, 9.7, compared to this number, 4.8, that I can either say that 4.8 is less than, because it's to the left of 9.7, or in the order that's given, the 9.7 is greater than the 4.8. So that confirms that this is our final answer. And here's that example typed up, which brings us to pencil problem number 12, which is shown in a separate video. And that's the end of lesson number 4.